Hello everyone, welcome to the channel. So today we will be discussing another very powerful ensemble learning technique called boosting. And if you've ever used decision trees and felt like the performance was not good enough, boosting might be the magic trick you're looking for. So if you remember from our previous videos, decision trees as such, they have a tendency to overfit, and that's why the generalization error is not good enough. And boosting, similar to bagging, is a technique to improve decision trees, right? So it leads to trees which have better generalization properties. And very similar to bagging, it can be applied to both regression and classification. But there's a key difference, right? So if you remember from our previous video, in bagging we perform learning independently. So what we had in bagging was a collection of data, and then we sampled from this data several other data sets. Let's call this D, the original data set, and the bootstrap data set. The first one could be called D1, then we had D2, so on, and we had Dn. And then on each of these n different data sets, we learned n different trees independently. Okay, so T1, T2 up to Tn. And then we combine these n trees to get our bagged model. Now, this is not the case with boosting. So we do not perform any bootstrapping or resampling whatsoever. We proceed sequentially. So we always have only the original dataset at hand, and we sequentially train models on this original dataset. So this is how it works. Let's look at an example. Okay, so let's say you have a one-dimensional input space denoted here by x, and a one-dimensional output space, so we denote it by y. And you might have a certain number of data points. Let's say we have 3 data points in this case for simplicity, and the average of these data points, or the average of the label values, would sit somewhere here. Okay, so this is the average of these 3 label values. So what you do in boosting is, first you make the crudest approximation possible. So you want to have a machine learning model f that takes as input x, and you set this to be y1 plus y2 plus y3 by 3. That's this average shown here in the plot, right? So this is the most crudest approximation you can have, and then you compute the errors made by f of x. So this is an error, this is r1, r2, and then r3. So this is the error you made while using this crude approximation. And then in the next step, you compute a model that learns how the errors behave. So what you do is you learn a model f tilde that takes as input x and provides an approximation for this error rx. Now just to clarify, rx here is nothing but the true label minus the model's approximation. Okay, so you're fitting a model here that approximates the errors made by the initial model fx, and then you just have to update fx using f tilde. So f tilde and f are combined to then improve upon f. So when we do this combination, when we perform this combination, what we are doing is we are fixing the errors made by f, and then we repeat this whole process on the same data set, right? So we never change the data set. On this data set that we have 3 points in this case, we repeat this process b times. So we start with this crude approximation in the first iteration, then we develop f tilde, we combine the two, then we have a new update for f, and then we keep on repeating this b times. And this is what boosting does, right? So you're slowly learning better approximation with each iteration. Now if you remember from the previous videos, this is unlike learning decision trees, right, where you learn the whole tree in one shot, and this is what leads to overfitting. So here what we're doing is we're progressing very slowly, and that's why boosting is called slow learning, because you only proceeding slowly and sequentially. So now let's look at the algorithm in detail. Now the first step of the algorithm is to define the dataset. So you have a dataset with some input features x, corresponding labels yi, and you have n of these points. Then you have your initial approximation, let's call it f of x, and that's nothing but the average of the different labels you have. Okay, so you just take the average of the labels. And then you also start with the initial residual, which is the true value minus the model's approximation at point I. Now let's write down our iterations for boosting. So the first step is a loop over different iterations we had. So for j in 1 to b, so we are repeating the iterations b times. So first thing is to fit a model f tilde on the input features x, which remain the same, and the residuals that result from our current approximation. So these are the same residuals that we have here. Okay. So then we have a model f tilde that is fixing, is trying to fix or learn the mistakes that f made. Okay. So once we have this model, we update our current approximation, and we do so via just adding f tilde to f. So as soon as you add f tilde to f, you have an update that fixes the errors we made initially. And this lambda here is the learning rate. And this is very similar to what you might have seen during stochastic gradient descent, right? So you have a learning rate, and this is what controls the speed of learning. I will discuss about this lambda and how to choose this later on after we have discussed the algorithm. And the last part is to update the residual, right? So we update the residuals here. And the residual now would be yi minus f of xi. Note that f here, right, the model that is being used to compute the residuals in the end is this updated model. It's not the initial model, but rather the updated model, and hence the residual here is also the updated residual. Okay. And finally, what the algorithm outputs is just the model f itself. So output f. Okay, so it's that simple, and you will see when you deploy this boosting process in practice, how efficient it is, how well it performs. Now three questions remain open: how to choose the value of b, how to choose the value of b, which is shown here, and how to determine the complexity of f tilde, right? So how complex should be f tilde? If you remember from our previous discussions, we don't want f tilde to be too deep, otherwise we overfit, and that's why usually having just one stump model is good enough. What we mean by one stump, if you have an input feature space with two features x1 and x2, so one stump basically means a tree that divides the input feature space into just two parts, so something like this. So you'll have a tree with just two leaves and one root node. So that's how the tree would be visualized, and based upon the value of x2 or x1, the decision would be made. And this is usually enough to provide us with a good approximation in the end, right? But be careful if you choose f tilde to be very complex. So if you keep on adding levels to this tree, right, then what eventually would happen is that you will overfit, because you are trying to learn from the mistakes of the previous approximation, and there is a risk of overfitting. The same with b, right? So when you're choosing b, if b is extremely large, then again you will overfit. So b should be chosen such that your generalization error remains reasonably low. Now lambda, on the other hand, this controls the speed of learning, right? So if lambda is really high, then you are learning all the errors very quickly. So if lambda is 1, for instance, then you learn upon the mistakes made by f in just one step. If lambda is smaller than 1, or very close to 0, then you're learning slowly. And if lambda is 0, then this iteration does not update f at all, and you can check this very easily. So if you put lambda equal to 0, f is just your past approximation, which is set here as the average of the labels. So lambda controls the speed of learning, and both lambda and b you will choose using a cross validation technique or a holdout set that is used to compute the generalization error or approximate the generalization error. Okay, so this is how boosting works. There are also other variants of boosting, and I won't be going into the details of this, and I hope this helps you to understand also the other variants of boosting. So let's wrap up this video with 3 key points about boosting. Right, first of all, it's an ensemble learning technique that learns from previous mistakes. Right? And it's very powerful in developing tree models that lead to good generalization properties. Secondly, it's the most effective when you learn slowly, right? So when you start with smaller trees, what I mean is the complexity of f tilde here is not high, right? So these are f tilde should be a small tree, and this leads to a slow learning process with a small value of lambda. And when you do that, you get the best possible results. So it's possible that you overfit with boosting, right? So if you use a very large value of b, or a very complicated model for f tilde, or if you use a large value of lambda, you might end up overfitting. But usually overfitting happens slowly and gradually, so it's much more manageable as compared to fitting one big decision tree on your dataset. So I hope this video helps you with getting a general idea of how boosting works. And with this framework, you'll be able to approach also other types of boosting methodologies. And let me know in the comments if you've used boosting already